Thank you. Hi, everyone. Thanks for having me here. I'm Yuan from UC Davis. Today, I'm happy to present our work on how to leverage LLMs to generate hypotheses and use graphs to evaluate these hypotheses. This work is joined with Yuan, who just presented, and Wang from UC Berkeley, who is a PhD student. So we know that empirical studies rely on hypothesis testing. We use statistical tools, regressions, or causal inference techniques to either falsify a hypothesis or otherwise we cannot support it, and which means that we cannot falsify it, which means that we support it. We know the procedure of hypothesis testing is formalized, like we rely on statistical tests, but for the generation procedure, it more often relies on our intuition or observation on small data sets or our understanding of existing literature. So typically, it's much more informal. So this provides potential for LLMs to help us to generate new hypotheses. We believe that LLMs have the potential for the following reasons. First, LLMs are trained on large and very diverse corpora, which means that if you put one single concept, it helps you to connect to different concepts that are relatively related, and it's very plausible that they generate some sensible hypotheses. Also, for many LLMs, when they are trained, they have higher weights on high-quality corpora like Wikipedia or research papers. So they typically have better embedded understanding of those scientific concepts. Moreover, the reasoning, especially causal reasoning abilities of those models are higher. It can generate hypotheses that have valid causal paths. But we are not advocating like we can just directly using vanilla LLMs to achieve this goal, because at the same time, they also have some challenges. The first thing is the hypotheses generated by LLMs are typically lacking like novelty and diversity. If you just ask the model to say generate a new idea on social media, you are very likely to get some idea like healthcare or something, which is well studied in the literature. This is by the nature that LLMs typically predict most likely tokens. So if you put some words as a seed and ask them to generate a hypothesis, it's very likely that the model generates some very well-studied hypothesis. Also, for those models, they do not necessarily understand what are good hypotheses. Although some different researchers may have different opinions on what a good hypotheses are, if you really have the requirements to ask the model to generate a hypothesis, they may not fully follow your requirements. This is because, like most of the time, if you have a very long and complex task for the current LLMs, they do not necessarily follow your requirements. Like if I want the hypothesis to be general, novel, and well-bounded, it's very hard for them to follow every single instruction. Also, if you want to generate a hypothesis that fits into a specific domain or topic, there is a problem of sparse training data. So although the models are trained on large corpora, on a specific topic or domain, maybe the model didn't really read so many tags on that specific topic. And in this way, if you want the model to really understand the literature or the very specific topic, it's very challenging for them. Finally, even if we have used the, say, GPT to generate many different hypotheses, it's very hard for us to evaluate the outcome. Typically, it relies on human experts to evaluate one by one to figure out what is the good hypothesis. But this needs a lot of human effort. So to partially address those issues, we propose a framework with these two goals. We want to improve the current LLM's ability in generate hypotheses. Also, we want to design metrics to evaluate those hypotheses using the techniques in graphs. Our framework has 3 steps: hypothesis extraction, generation, and evaluation. So the first step is we extract existing hypotheses from literature. That has 2 purposes. One is like for the step 2, we're going to fine-tune the model using the hypothesis we have extracted. And the step 3 is also we prepare the hypothesis for the future evaluation procedure. So what we did is, given the existing literature data, like the previous abstract, we extract the causal hypothesis. We represent the existing research questions as propositional logic, which are connected by these 3 symbols, like and, lead to, and the negation, which represent most of the common connectors in a modern hypothesis. Those logics are also used to connect between different variables. Each variable represents a scientific concept. Because we want to have a structural data, like if 2 different papers talk about the same thing in different names, we want them to be matched. So we match all of the scientific concepts to a Wikipedia entry. So as an example, there's one hypothesis that is like teenagers uses social media causes the reduction in their attention span. So this is for the second step, preparation for the second step, fine-tuning. We also establish a hypothesis graph for the evaluation step, where we have nodes that are the variables and the edges, which represent whether those variables have co-occurrence on the same hypothesis in the historical data. This could be directional, like we have the causal relationship, or we can just simply do an undirected graph. Here's an illustrative example of hypothesis graph. This is just some small number of papers on online marketplaces. You can see that because this is related to online marketplaces, it is at the central, but we also have some other nodes like e-commerce, reputation, or social network that are also relatively central on the network. So the second step is, after we have extracted the hypothesis, we fine-tune an LLM using those hypotheses. So for those of you who are not familiar with fine-tuning, it means that given the existing model like GPT-4, we further train it on the data we have, like the hypothesis we just extracted. In our study, I actually just trained it on the existing abstracts, say all the ISR papers. And then we asked the model to generate new hypotheses by providing a seed. Say we asked the model to generate a new hypothesis on social media. So in this way, we can have many, many new hypotheses generated by our fine-tuned model. The last step is to filter out what are the good hypotheses. So as I mentioned, that it's very costly to rely on human experts to filter out what are the good hypotheses. So we designed some metrics to achieve the goal. Here we follow this paper to design 6 different evaluation criteria. I just want to know that there is a trade-off between generality and boundedness, which means that we want the hypothesis to be broad enough to have some broad scope, but at the same time, it should have some specific focus on a small area. And the convergibility means that we want the new hypothesis to be well integrated to the existing literature in a specific domain. So here are some graph illustration of the metrics. For novelty, it means that if we have a new hypothesis that connect, say, the 3 nodes here, we are calculating the average distance between any pair of the nodes that are in the new hypothesis. So here you see that the 3 nodes are originally far from each other on the network. So it means that it's likely have a higher novelty. Commeasurability is also based on distance, but it's slightly different. It means that after we have added this new hypothesis, how other nodes' shortest path have been shortened. So you can see that if we add a link between these two red nodes, the distance between other pairs will be shortened, which indicates that it might have a higher commeasurability. Generality and boundedness are trade-off. They are both measured by centrality. So we want to have a hypothesis that have some variables with large centrality, like it's about, say, social media or about online marketplace, that is important enough to a specific field. But we also don't want the hypothesis to have just some basic general terms, like a buyer, seller, it leads to like price, increase in price, something like that. So we also want some variables to have a small centrality. Relevant is about whether this hypothesis is relevant to a specific domain. So say we count the number of prior papers, say in information system or marketing, on what you have generated in the hypothesis. So our work is still in progress, so I just present some preliminary evaluation results. Currently, we focus on the IS literature, like we extract papers from ISR, and we establish the graph, and we showcase by the seed online marketplaces. So this picture basically talks about how our work, how our model generates more and diverse and novel hypotheses. So the red dots are the variables generated by our approach in a low-dimensional space after we have done embedding. And the blue dots are from the vanilla GPT-4o. So you can see that the distribution of our approach show more like diversity because it's more spread out on the three-dimensional space. But for the vanilla approach, it's more focused on the in the center. We also did some evaluation from both human experts and the LLM. So what we did is we first generate about like 100 hypotheses, and then we calculate the score by all the metrics we have proposed, and then we rank them from 1 to number 100, and we just focus on the top, like among the top 5 or 10 or 20, we asked the model and ourselves as a human evaluator to evaluate the score. We show that at least in the hypothesis we have generated, the average score we have here is much better than the vanilla approach. So this shows that our approach is promising in generating at least better quality hypotheses than what vanilla LLMs are able to do. In the interest of time, I just show you one illustrative example of what our approach generates and what vanilla LLMs generates. So you can see that the top one is what our approach would generally generate. It has more like focused terms, and the hypothesis is in general like less intuitive. But if you just ask the GPT, like GPT-4o, to generate a new hypothesis on online marketplace, what they typically tell you is like some common sense, like if you do effective marketing and if there's a moderator that is user traffic, how the sales will be increased or satisfaction of customer will decrease. So with that, let me conclude. So we propose approach to fine-tune LLMs to increase its ability to generate novel and diverse hypotheses, and it also cares about a specific domain. We evaluate the hypothesis using graph metrics. We're still developing new metrics to try to further make the evaluation process more fine-grained, but this shows that this kind of approach is promising. So we have some future directions here, like how to utilize larger corpora or design other graph or NLP-based metrics, And eventually, we are going to evolve more human experts to help us to do the evaluation procedure. With that, I'd like to thank you for your attention, and I'm happy to take questions. Yeah. Awesome.
Great presentation. I'm just wondering, like, as an alternative way to test the performance of this of your framework, is it possible to kind of test to what extent the newly published works, their hypotheses, kind of overlap with the hypothesis that you're proposing? Hopefully, the newly published work, or even like the working papers, they might not be already included in the training data. So in this way, if there is a higher overlap, maybe that's a different way to suggest the performance of the model.
Yeah, that's a very good point. We have thought about that. One current challenge we have is the current data set doesn't really have the newest papers, so we need to further grow the new data, the new papers. The other challenge is, like, if we focus on, say, working papers, we don't really know the quality of them. So it's hard to really say that, okay, this paper has is a better hypothesis or not. But I see your point. Like, we can definitely evaluate on the newly published papers, or at least to show, like, among the newly published papers, what are the metrics and whether the hypothesis we have generated match the distribution of the newly published papers metrics.
Time for one more question.
Great, thanks. I have a quick question about the independence of your evaluation metrics, because you have the average shortest path, as I think it was novelty. So if you have a literature stream that is very dense, let's say platforms, it will have an effect, I would guess, on commensurability and also relevance, because relevance was a function, I think, of the number of papers in that area. So then I would expect that the evaluation metrics are not really independent across these 4 different streams.
Yeah, that's a very good question. So your concern is, like, the metrics we have designed should be somewhat correlated, and they're not independent from each other. So one way we can figure out is we run a regression or some other techniques to at least make them less independent, and then we calculate the total score. So in this way, we have both the overlap part and also the orthogonal part in the evaluation procedure. We haven't examined that detail in such a detail at this moment, but yeah, we are definitely going to work on that to try to figure out how to address the independence the issue here. Thank you very much.
All right, thank you so much. We now have a break from 10:45 till 11 o'clock, and then we'll be back in here in the room 612 at 11.